Yeah, I haven't. I appreciate the introduction if you don't mind,
Oh,
but
that's quite all right. I'm so sorry. I didn't
sorry
realize.
if she makes you blush.
Yes, it made me blush, I have to say.
Well, there's more. So he's also an industrial consultant in the area of machine and robotic system design and provides testimony on intellectual property and product liability. He served as Chief Technical Officer of Accuracy Incorporated to assist the transition of robotic radiosurgery system from research to market. In 2010 and 11, he served 2 terms as chair of the Board of Governors for the Southern California section of SAE International and is the 2012 secretary of the Orange County Engineering Council. Over the past 15 years at UCI, he has focused on developing engineering leadership through student design and execution of major engineering projects, and is the director of UCI's Performance Engineering Program. His introduced project engineering courses for graduate students, seniors, and freshmen at UCI, and provided course materials for race car engineering courses in local high schools. And then just another note, like so many theses that I've looked through as we're trying to develop this course, have had his name as advisors to the students, and a lot of the professors that we've talked to were worked with him as students, and so he's been a great mentor, and that mentorship has trickled down to help us even over here at BYU. So thank you for all the work that you've done.
I've actually been blessed to have so many great people to work with, including Professor Howell. So nice to meet all of you. All right, so I've had the pleasure of interacting with Ivy and her students and Professor Halverson. And one of the things that sort of came up on a regular basis was this notion of how quaternions are useful for getting around gimbal lock. And I wanted to just take a minute and look at what, I guess I have to share my screen. Give me a second here. Okay. I just wanted to take a minute and look at what gimbal lock might be, and then ask why quaternions are associated with gimbal lock. Because what I really am hoping to do is to move you in a completely different direction and realize that quaternions are a mathematics or an easy entry into a mathematics that is quite interesting and broad. So this is I'm showing you on the screen, I hope, the Wikipedia page for gimbal lock. And if you look at the gyroscope as just a 3R robot, a robot that has 3 revolute joints that happen to all intersect at a point, then you realize that gimbal lock is nothing more than a singularity. The same sort of thing happens with a Puma robot when the wrist joint becomes just above the shoulder joint. Your ability to use those degrees of freedom to position the robot decreases because it's in a singular configuration. Now, one way to look at this is to consider this as a reduction or a sort of a failure of your coordinate system. The coordinates you're using to position the end effector have failed you. They've aligned up, and they don't now give you the coverage that you think that they should. The simplest way to visualize this is to think of latitude and longitude coordinates on the surface of the Earth. They work great everywhere except at the North Pole and the South Pole. When you're at the North Pole, you're at latitude 90 degrees and you've got no longitude. You're at a singularity. And it's not, it's just a problem of your coordinate system, and you can fix it relatively easily by shifting your coordinates. And that's essentially how quaternions have become aligned with gimbal lock. Gimbal lock showed up long before robotics in the trying to navigate using a compass. And the way to get around it, at least mathematically, has always been to change the parameters of your coordinate system in the vicinity of Gimbal, in the vicinity of this singular configuration. And we do that with robots too. When we get near a singular configuration, we have to change the coordinates. We know where it is, so we just have to plan for it. All right, now what I'm going to do with that as an introduction, I'm now going to start looking at quaternions, and let me show you the end, where I want to go. So if you go all the way to the end, now unfortunately I didn't give you these particular slides. I will update the deck that I sent you, but this is where I want to end up. The mathematics of quaternions is an easy entry to what's known as Clifford algebras. Clifford algebras provide a broad tool and versatile tool for all kinds of activities. I think when I met with Ivy and Professor Halverson and the group, we talked about it informally, but I thought I would take a minute to point you to some papers. So there is a nice theory for kinematic synthesis that rests on Clifford algebras. It's also possible to sort of think of planar motion as though it was really a special case of spherical motion or rotational motion in 3 dimensions on a very large sphere, exactly like you would think. Our everyday planning of mapping assumes the world is flat, but we know that we happen to be on a very large sphere. You can actually very smoothly move the mathematics on the sphere into planar mathematics and work back and forth to use geometry on the sphere to solve some problems that show up in planar kinematics. That technique works exactly without change on mapping or shifting a sphere in 4 dimensions, a hypersphere, which has a 3-dimensional surface, flattening that out until it becomes a 3-dimensional space. So we can actually think of 3-dimensional space that we work in as a localized section of a sphere in 4 dimensions. And if you do that, then you actually can solve some real tricky problems in robotics and computer-aided design and geometric modeling that have to do with the interpolation of spatial motion and in averaging spatial displacements. For example, if you had a bunch of spatial displacements and you wanted to find the center of those spatial displacements, that's actually quite difficult to do unless you lift it to working on a sphere in 4 dimensions. Then it becomes quite simple. The mathematics that allows you a very convenient approach to that kind of theory are known as biquaternions and double quaternions. They're actually 2 names for the same thing. And that was studied by some students of mine in the late 1990s. So the idea of quaternions here really that I'm going to try to lay out for you really is a rich direction for the solving rather challenging problems in kinematics. All right, so that is my introduction. And this is let's see, I got to get to the beginning. Okay, here is my overview. This gives you an idea of what I'm going to present. Let's see, set it up so we can see it easier. Maybe you can. I'm not quite sure how this shows up on your screen. The font is a little bit small, possibly. These are the topics I want to cover. I don't have a cursor, so what I'm going to do is I'm going to go back. I'm going to leave it in this mode so I have a cursor, and then I can actually move things around. Oops, I don't want to do that. Okay, here we go. All right, so if you don't mind, I'm going to leave it in this mode. I can also allow me to edit it if I find errors, and also maybe type in some notes to answer questions. So All right. The very first thing I want to talk about are what is known as eigenvalues and eigenvectors. And you guys have studied this. This is like, I think I mentioned this when we met previously. When you take a linear algebra course, any linear algebra course, you spend probably half the time solving linear equations, trying to prove that n equations and n unknowns has a unique solution. That generalizes. You can do n equations and m unknowns, whether n is bigger than m or less than m, and all this kind of stuff. Sometimes you cover that, sometimes you don't. But really, when they really do move to relatively quickly is how do you solve the eigenvalue problem? And nobody tells you what the eigenvalue problem is because they spend all their time trying to get you comfortable with that mathematics. The eigenvalue problem in kinematics is absolutely central because it's the mechanical joint that allows movement. So, for example, a hinge of a planar linkage is the eigenvector of the rotation of that link. A screw axis or a cylindric joint or the revolute joint of a robot arm is the invariant or the eigenvector of the transformations of these two joints relative to each other. The mathematics, I mean, it's kind of nice. Kinematics gives, and robotics and the design of machines give a physical representation, or what is, at least in your linear algebra class, a rather abstract concept. And we're going to need that because it's so central to everything we're doing. It shows up quite naturally in quaternions. And that's, and for a reason, okay, I can't say that I know why quaternions represent the mathematics of invariance so nicely. It's simply a fact that it does. I haven't gone that deeply into it, but I'm hoping today to be able to show you the geometry that is at the core of the use of quaternions in kinematics. Okay, but I'm going to do that by a rather circuitous route. I'm going to go from eigenvectors to Cayley's formula to Rodrigues equations to Euler parameters, and finally get to Rodrigues composition for rotations. Now, Rodrigues wrote this paper in the mid 1800s. It's a very famous paper. The paper is probably, if I remember right, close to 80 pages long. And he does the composition for rotations in the first half of the paper. He then goes on in the last half of the paper and does the composition, the same analysis for the composition of spatial displacements, which is absolutely remarkable. It is, however, because the mathematics is so convoluted, I mean, it's really detailed. He does everything in component form. It's kind of lost, but it was really helpful to me when I was really focusing on this specific point. All right, so once we get to Rodrigues composition of rotations, we basically have the results that I want you to be aware of. When you have that formula, all of a sudden now you've got quaternions that were invented by Hamilton. Hamilton's definition of quaternions, whether he knew it or not, happens to encode very directly Rodrigues' formula for the composition of rotations. All right, now that's it. That's really the message. I'm giving you away the message at the beginning of the talk. I want you to understand that when you multiply quaternions, you're actually encoding the composition of rotations. If you're multiplying dual quaternions, you're encoding the composition of spatial displacements. The geometry of the invariance is encoded there. When you do it in double quaternions, you're doing it for rotations in four-dimensional space. When you're doing it with planar quaternions, you're doing it with the composition of poles in the plane and complex numbers. But in order to make this, at this point, you now have kind of if you think about it a little bit, you got planar quaternions, dual quaternions, double quaternions, all of which seem to have a kind of important geometric core. How are they related? I mean, is there any relationship between all of these things? Well, it turns out about the same time that Hamilton presented his theory and wrote his tremendous book, and Tate came along later and did more. William Kingston Clifford put together notes. He actually wrote notes for his classes that introduced quaternions, and he did it in a very organized way. I mean, and it was in. He got to the point where he said, "Look, I think we can do this, and we can make all of this simple." And he came up with a simple rule, Clifford's product, that instead of defining everything with component-wise like Hamilton did, he said, look, if I just introduce this rule, I get Hamilton's quaternions. And not only that, I get complex numbers. Not only that, I get a whole bunch of other things. And he went on sort of describing all the other things that we now call Clifford algebras. And that's probably the next message I'd like to get across to you. But we are venturing at this point into mathematics that is probably less familiar, specifically multilinear algebra. So most of us are taught linear algebra, but multilinear algebra is got a weird, it's got a weird sound. The mathematics is not complicated, but it sounds weird and it looks a little weird. So it would be fine if you don't follow much beyond this point, but I think it would be okay as long as you knew about it, and then you could pursue it at your level of comfort. Okay, then out of these Clifford algebras comes the even Clifford algebra of three-dimensional space. This is the Clifford algebra definition of quaternions. Now, I take a little aside here, and I want to tell you that probably no one uses, Clifford's I, J, and K to multiply quaternions. That's multiplying things component-wise. I mean, it's just too complicated. Most everyone uses a matrix version, a linear operation version of the quaternion product. It just makes everything simpler. And then I just want to address another aside, which is that once you can multiply things, if you think of a quaternion is something that you can add as well as multiply, once you can do that, you have got a whole lot of things you can do. Most obviously, generate exponentials, but you can generate other functions as well, infinite series of functions. And so the infinite series of these items, but the one that's particularly relevant to kinematics is the exponential function, which transforms a Lie algebra into a Lie group. And again, I'm not going to go into any of that, but you can see that this opens a path towards other things. And that's it. That's what I'm doing. So that's my overture. Let's begin. Before I get started, maybe it's worth asking if there's something you might want me to make sure I touch on as I move through this. Or have I already blown you away? Is Ivy sleeping in the back over there?
I'm still awake. I'm here.
She's in the front.
Okay.
I think it all sounds pretty good. Yeah, this looks awesome.
All right, let me do the best I can. All right, see if I can now deliver on the promise. Okay, first things first, what do we mean by the eigenvector problem? Okay, so this is the way the eigenvectors are usually introduced. Now, in our case, kinematics, we want AX equal to X. So in other words, we want to know what points in the moving body don't move. Why? Because we want to use those as hinges. We want to use them as sliders. We want to use them as mechanical elements. So we want the coordinates of that point to be the same before and after the transformation. But that's not the way the mathematicians present the eigenvalue problem. They present it as ax equals lambda x, where lambda is a constant. So for them, it's okay if the transformation expands the vector or shrinks the vector. We want it to be the same, but they don't mind if it expands or contracts. They still consider that an invariant. So we want to solve this problem for the specific case of lambda equals 1. In other words, we require our rotation matrices to have an eigenvalue equal to 1. So the question is, do they have an eigenvalue equal to 1? Well, let's just check. Well, the standard approach is to simply say, if you look at this, I want to solve this matrix equation. It has an obvious solution. X equals 0 is an obvious solution. So that's often called, because it's so obvious, the mathematicians call it trivial. I don't think it's trivial. I think something equals 0 is kind of a good thing, but it's not going to be useful to us. So we want something other than 0. So in order for something to have a solution other than 0, we realize that the determinant of this matrix has to be 0. 3 by 3 matrices it's easy to expand the determinant. And then furthermore, if you require that it's a rotation matrix, you've got extra conditions. You know that the determinant is 1. You know that the minors equal the elements. These are things you may not know about rotation matrices, but they're actually kind of cool things. And they come out of the very obvious requirement that the columns of the matrix have to be unit vectors and they have to be orthogonal. Anyway, so once you do that, you get this very straightforward third-degree polynomial you have to solve. You plug it into Mathematica, bang, it's done nowadays. Okay, it's easy. And you find that lambda equal 1 is indeed a root, which tells us that our friends who are our mathematician friends are right. The rotation matrix has an invariant. Of course, we knew that already, but it's kind of nice to bring the mathematics together. And in other words, and the other remaining roots are complex numbers, and those complex numbers define the rotation angle. Those complex numbers actually combine to define the plane perpendicular to the rotation axis, and the eigenvalues define the rotation. All right. Now, we're going to go a little bit further with this, with something you may or may not have considered. All right, so we have a rotation matrix, and we're requiring that rotation matrix to maintain the distance between any point that it transforms. So if I rotate this segment from here to here, the distance between the endpoints of the segments don't change. What we can do is we can now look at that and turn it into this equation where we're simply saying the measurement from the origin to the x after the transformation is equal to the distance from the origin to the x coordinate before the rotation. This can be manipulated into this expression. This expression says that the distance between the before and after, so the negative, you subtract one from the other, and then from the sum, you take the difference and the sum, and what you're doing is computing the diagonals of a rhombus. And this equation from this step to this step simply says that the diagonals of a rhombus are perpendicular. Nice geometric relationship. And you can even go further. You can sort of manipulate this and discover that I can transform the sum into the difference with a matrix operation. This matrix operation can be shown to be a skew symmetric matrix. So the operator, this B matrix that I have constructed from the actual rotation, performs the operation of transforming the sum, the vector that's the sum, into the vectors that's the difference along that rhombus. I thought I had a picture of it. Oh, it's on the next page. Okay. Anyway, this is by following these steps, you wind up getting, you can now invert it, you can solve it, you wind up getting an equation for the rotation matrix. And this equation for the rotation matrix is an explicit parameterization of the rotation matrix. You know that it's got 9 coordinates, 3 by 3, and you know that because every column vector has to be a unit vector and they have to be perpendicular to each other, you get 6 constraint equations. So you know, at least in your mind, that you've got 9 coordinates with 6 constraint equations. There's only 3 degrees of freedom. This formula, Cayley's formula, gives you an explicit equation with 3 variables, the 3 components of that skew symmetric matrix. That is a very explicit presentation that rotation matrices in space have 3 degrees of freedom. All right, now let's go a little bit further. So that's known as Cayley's formula for a rotation matrix. If we go a little bit further and we realize that the multiplication by a skew symmetric matrix is the same as the cross product using the components of the rotation matrix assembled in a particular way. You can take the components of, I didn't write down what that rule is, but I think if I were to challenge you to prove that the matrix, the skew symmetric matrix times y was equal to vector b crossed into y, you would be able to figure out, which element was which in that skew symmetric matrix. This equation, even though it comes directly from the calculation for Cayley's formula, this is known as Rodrigues equation, and B is known as Rodrigues vector. Now, Rodrigues ends in S, so when you make it plural, you put I think, at least I'm not 100% sure. Okay, so when you say Rodrigues, it sounds like possessive, but his name ends in S. This is actually the formula he uses. He constructs this formula, and then he uses the geometry that this formula represents, which is the rhombus, for compositions of rotations. He generates the rhombus again, and then he generates the rhombus for the composite rotation, and from that derives his formula for the composite rotation. So this was a very central tool to his derivation. I'm not advocating it for use in mathematics of rotation matrices. I mean, we use matrices. Matrices are a very powerful tool. And in fact, many mathematicians or many engineers, not necessarily mathematicians, will tell you, why are you wasting your time with all of this quaternion stuff when we can do it all with matrices? And that's a very valid question. And my response is, I would always do it with matrices. Okay, matrices are very easy to program and compute. And so I would never abandon matrices. I use the mathematics of quaternions and Clifford algebras to help provide a perspective on the calculations that I can't get from matrices alone. All right, if you go through this, I'm not going to go through this in detail, but you can figure out the geometric meaning of the components of Rodrigues vector. It is tan of the half angle, which is the vertex angle of the rhombus. So the vertex angle is phi. Because you're taking half of it with the diagonal and you're rotating it, you're actually using tan to the half angle. And the unit vector along B is the Sx, Sy, Sc. So this has a very meaningful geometric definition. These are known as Rodrigues parameters.
Sorry, Dr. McCarthy, could you slide over a little bit so we could see the picture of the rhombus?
I didn't. Oh, gosh. I knew I had a picture somewhere. There we go. How's that?
Yes, that's awesome. Thanks.
Okay, good. Yeah, this is the vertex angle right here. And because you're going from the one diagonal to the other, you're actually using the half angle of the rotation. All right, good. Thank you for pointing that out. Okay. I didn't know exactly how to handle this other than just to put it up. So if you go back to the definition of this B matrix, and we now know that it is the tan of the vector skew symmetric vector generated by S, you could actually realize that you could factor out tan of the half angle and multiply it times the skew symmetric vector S, which is constructed from a unit vector. And if you have tan, you have sine over cosine. And if you're multiplying by an inverse, and you could actually factor out these terms, okay? And it turns out if you factor them out, you factor out the tan, and you've got a tan on the top and tan on the bottom and a tan on the inside. The tans that you factored out cancel, but you've got tan on the inside. And now you can see that you can multiply through by sine and cancel. And when you do that, you wind up getting an expression that looks like this. So it's relatively easy, but I have to wave my hands. I want to sort of move through a lot of the calculations that we're doing and leave it to the students as an exercise, if you will. You can easily transform Cayley's formula that relies on the skew symmetric matrix B and into this form, where you've got the explicit representation of the rotation angle. It's actually half the rotation angle, and the skew symmetric matrix constructed from the unit vector that defines the rotation axis. Once you've got this, you can now go to, once you've got this, you now have an explicit representation of 4 parameters, not 3. You've got cosine, you've got sine times the unit vector and then cosine by itself. These 4 parameters are known as Euler's parameters for a rotation matrix. All they do is really take the 3 Rodrigues parameters and add a 4th to get rid of the sine term in the denominator. If the sine term in the denominator is 0, in other words, if the rotation angle is 0, what happens to Rodrigues parameters? They become a problem. Well, so by taking out the sine and having a cosine term separate, you can actually handle that. You don't have a problem when cosine becomes 0 or sine becomes 0. The Rodrigues parameters are a coordinate system for rotations that get rid of the singularity when phi goes to 0 or phi goes to 180. So it's these set of parameters that aerodynamicists or control theory people have found helps to parameterize rotations to get around gimbal lock. So whenever anyone says, well, I'm going to use quaternions to get rid of gimbal lock, what they're really talking about are these set of parameters, Euler's parameters. Now, we're going to see, and let me just take a minute here. Well, let me just jump to it. No, I'm not. I can't. I'm just going to tell you right here now. These parameters are the parameters that define a quaternion. That's how quaternions became bound with gimbal lock, because these parameters are a convenient set of coordinates for spatial rotations that avoid the singularities. The trick, if you think about it, the way they got out of the problem was by adding a coordinate. you actually have gone from something that has 3 degrees of freedom, and you've added a fourth to give you the flexibility you need to avoid the singularity that's associated with those 3 degrees of freedom. Standard trick in mathematics, standard trick to get out of situations where your geometry has some sort of singularity. You add a dimension, you lift the dimension, and it works very well. It works across the board. Okay. Anyway, a little bit of calculation will show you that this expression for the rotation matrix yields an expression that you may be very familiar with. This is the expression of a rotation matrix in terms of the rotation angle and the skew symmetric matrix that tells you the rotation axis. I didn't put it in, but this equation is also equal to the exponential of the rotation angle times the skew symmetric matrix. So you can actually think of this as an exponential, which is the Taylor series, or the series expansion, the identity matrix plus phi times s plus phi over 2 phi squared over 2 times s squared, and on to as the exponential series. And when you collapse all that, it takes this form. All right, now some geometry. I didn't know how to do this either. I have a long derivation for this in my book, and I don't want you to go through that derivation. I don't even want you to go through. I do it 2 ways. I do it using Rodrigues' formula, Rodrigues' equation to get to his formula, but then I also tackle it just in the raw geometry. If I have 3 vectors in space, and if I have a triangle, if I have 3 vectors in space, A, and B, how can I use the geometry of the angle at B and the angle at A to calculate the vector C and the angle at C? Now, this is a classic geometry problem. It's called triangularization. In other words, if I know where I am at A, and I know where someone else is at B, and I know the angle between us, if I know this angle delta between us, and then I measure the angle from B to a source of a signal or something, and B does the same thing, then between us, if we just work out the geometry, and it is completely explicit, it's a bit of a challenge, but you can just work out the geometry, we can find C. So this kind of triangularization we talk about all the time. You can do it on the plane. If I know this point and that point, I know the distance between us, and I know the angle at each of those points, I can now intersect them and find the point of their intersection. So that ability to take information at 2 points on a triangle and calculate the information at the third, it's a nice geometric tool. You don't need any special mathematics for it. You just got to go through the details of the coordinate geometry. Now, back to Rodrigues' formula. If you represent, this, if you consider this, you don't have to, but if you consider this as the rotation axis, the axis of a rotation that rotates by alpha over 2 from this side of the triangle to that side of the triangle, you can write it as Rodrigues transformation, Rodrigues equation. And then if you do the same thing at B, you say that rotates this side of the triangle to the other by amount B over 2. And then you can have the transformation from around B using Rodrigues equation again. Now, if you step back and you say, well, this is the composite rotation will have a eigenvalue. It'll have a rotation associated. It'll have a rotation axis associated with it. It'll have a rotation angle associated with it. The question is, where is it? Now, there's no reason to think that it would happen to be right where these two great circles intersect. There's no reason to think that. So let's calculate it out. And so what happens is when you do the calculation, do this kind of manipulation, you can actually come up with an equation that says I can go from this position to the final position, the small x to y to big X, with a rotation of the amount gamma over 2 around the axis c over 2. Axis c. And it happens to be this axis. It happens to be the intersection that defines the triangle. Now, the definition of this axis is a little bit intimidating. All right. It is actually this formula, and it is very common. I mean, I don't pretend that this looks like something that you would want to use every day. In fact, when Rodrigues presents it, he presents it component-wise. And I would say in this form, it looks a lot easier than it does when it's written out in component form. But this is Rodrigues' formula, and it is proof that the composition of two rotations yields a axis that forms a triangle, and that the internal angles and satisfy a equation related to the external angle at C that's represented here. And I'd like to just pause here, because this really is the core of what I'm going to be trying to present to you. This is probably the most complicated series of steps in what I'm talking about. From here on out, things are going to get a little bit simpler. So maybe I could just see if there's anyone who has collected any thoughts or would like to know anything.
Well,
No.
I like simpler. We have about 5 minutes left, so.
All right, here it comes.
Yeah.
All right. This is it. This is the end of the story. 5 minutes. William Hamilton introduced quaternions to generalize three-dimensional geometric properties of complex numbers. It was well known that complex numbers perform geometric operations in the plane, and he wanted to come up with an operation that would do the same thing in three-dimensional space. He spent a long time trying to figure out how to do it with three numbers, because that's what you use to define coordinates in space. It was the breakthrough when he realized, I can't get that to work. I'm going to see what happens when I move to four numbers. And when he moved to four numbers, it worked beautifully. And in order to make it work, he introduced this rule, this operation. When you think of Hamilton, you think of him as writing I, J, K and multiplying I times J so it equals K, and that I squared is minus 1J. And that's all absolutely correct. But when you actually look at what his rule does, what he's doing is he's taking a scalar plus a vector, because he's using four parameters. And he multiplies the scalar times a vector, and he gets a rule for that. When you multiply these two sets of four things together, you get four things. You get a scalar and a vector, and that scalar and a vector has this structure. What you get if you happen to use cosine phi over 2, which should be familiar to you by now, sine theta over 2 times the unit vector. This is now Cayley's parameters for a rotation. If you happen to now represent those four parameters this way and multiply them, you just multiply them following his rule, what you get is exactly Rodrigues' formulation. So what this tells you is that quaternions encode very explicitly the operations of a triangle in three-dimensional space. Okay, and even more, If you specialize quaternions to the plane, you get you encode operations on a planar triangle. If you generalize quaternions to space as dual quaternions, you encode the operations on a spatial triangle, which are the invariants of spatial displacements. And even further, if you encode the operations in a four-dimensional rotation, you get double quaternions. And the only thing that I've left out at this stage is how you represent all of these things using Clifford's rule, Clifford's approach, using this Clifford product. But I can leave that as a exercise to the students. You'll enjoy it when you actually do it. I'll end there. It's a pleasure talking to you. Thank you for your patience with my random walk through an area of mathematics that I have found incredibly fruitful for me and my students, and I think has got even more opportunities in the days ahead. Any thoughts, any questions?
Just thank you so much. The big picture of how all this fits together is extremely helpful. I think some of the details, it's going to take us some time to unpack. That big picture is really helpful.
So I'm seeing on the student screens some versions of this slide. So do you already have?
Yes, yeah,
Yes, okay.
yeah.
Yeah, and I got an updated one that I need to give you to post. So
Cool. Thanks, that
All right.
sweet. I just had a quick question. Hopefully it's a quick question. So I've seen lots of quaternions, know what they look like as four elements. So does a dual quaternion look much different than that? Does it still have
Oh, I know. The easiest thing to do is I actually wrote this I actually had a period of my time where I was really obsessed by Wikipedia. So I actually wrote some of this section on where I provided some examples. I think it's here. Okay, I'll get down to base. I think there's some. Here it is. So the examples of real and complex Clifford algebras. I actually wrote these out. So let's see. There's complex numbers. Let's see. Here are the examples. So these are the examples that I wrote out. I did it for quaternions, and I did it for dual quaternions. So you can sort of see. Now, I mean, these are things that are sort of scary if you've never seen them before. These are known as multivectors. You can actually pack multivectors side by side. It's not complicated. It's nothing more than a matrix that has each of the vectors as a column, and that's a multivector. We don't present it that way, but that's really what it is. And then you actually can multiply them and in special ways, but don't worry, don't let that worry you. This is an example of a dual quaternion.
Okay.
And it's in my book also. The dual quaternions look the same as a rotational quaternion. We just put a hat on it, and you just have pairs of numbers. Anyway, is that an answer to that question?
Yes. Yeah. Thank you.
Mm-hmm.
Okay. Thanks so much.
Great seeing you guys again. Thank you for your patience with me, and thank you for your interest in something that I've found to be a lot of fun over the years.
yeah, thanks, and we'll be keeping in touch. Appreciate your time.
It's a pleasure.
Hey, thank you so
Thank you.
much.
Mhm.